So what are the methods to be used to analyze this data? So the method that is to be used to iteratively find it out. Okay, just put the data whatever we have with us and just find it out what is the values of these three parameters. So iterative procedure is one that is very often used. The number of iteration depends on how quickly the parameters converge. So for any optimization problem, we end up with the convergence of the parameters, and how quickly we get these parameters converged will tell us how many iterations are required. The converged parameters are close approximate of the three parameters. They may not completely represent the actual values. They might be very close to what we are expecting. The likelihood of the nonlinear regression is maximized when the residual sum of the square is minimized. So here also we just define a loss function. We define a loss function which takes care of y minus x. X is your independent variables and some sort of a beta, right? Here we have beta and then exponential term theta. Um, T by theta. Okay, so that's the loss function, and you can actually take the square of that, which gives you the residual sum of square. So iteratively you find out the beta naught, beta 1 and theta for which the residual sum of square or the loss function is minimum. So that's the way you optimize the algorithm to find out the parameters values. There are three ways of computing the parameters. One is the direct computation method, second one is the derivative method, third one is self-starting method. Now we'll see what these methods are. In the direct computation method, we initialize with the values of beta naught, beta 1, theta by inspection of weight loss data. Okay, so initialization of the parameters are done by just manually inspecting the weight loss data. Weight loss is the dependent variable, right? Yes. So this is the R code that we have with us. We sort of assume beta naught, beta 1 and theta to be taking some values, and these values are purely given from the data that we have with us, and then we fit the model, the model that we just saw in the previous slide, and we do that iteratively and find at what value of beta naught, beta 1 and theta we're getting the minimum of the loss function or minimum of the residual sum of square, and that's the way we find it out. Then the second one is the derivative method. In derivative method, as you know that you use derivatives to find the minimum value of function. For instance, if you have x square minus 2x plus 3 and that's y, you can actually find out the minimum value of y by taking the first derivative with respect to x and then second derivative with respect to y and seeing if it is negative or positive, and then put that some value of x at that point and you get the the minimum value of y. So that's what we have learned in school calculus, right? That's exactly what is being used here. So here is the equation and the tangent plane to the surface. Tangent plane is nothing but the first derivative at a coordinate point beta equal to beta naught is where we have got a mean vector and then offset vector, and then there is a matrix which defines the tangent plane. Each iteration gives us a new approximation of beta until convergence is reached. Pretty much like this last procedure, we also are approximating the value of beta, which gets changed in every iteration, and you get the converged value after a few number of iterations, depending on at what point you get the optimal value. So the derivative method uses numerical methods instead of random guessing in the previous method, right? We just guessed randomly to compute the formula of gradient unless first derivatives are supplied. So if you do not supply the first derivative to the algorithm, it is going to calculate the gradient of the function, and that is being used to find out the final value. So you can use the R code in order to be able to do that. We won't get to the details. All we can do is that we use the derivative function within R, which will do the job for us. Okay. Then third one is the self-starting method. The self-starting method fits a nonlinear model without explicit initial value. So that's one thing to be uh, take a notice of how it is different from the other two. So it fits a quadratic regression. So it assumes the quadratic of some form, and then it fits the regression. And it finds out the initial value of theta using some formula, and that's we not see. So what is important here is that find initial values of beta naught and beta 1 by obtaining linear regression of y with respect to the exponential. So the exponential term is being now replaced with some sort of another explanatory variable, and you just find beta naught and beta through linear regression, and then finally you express your theta naught value over here and you get the theta. So that's self-starting method, and you can also do that using R. Okay, so you can write a self-start procedure. You can that's going to help you out, finding the optimal value using this method. So end of the day, what matters is the final values of beta naught, beta 1 and theta, and that they should ideally be the same. And also what matters to you is the number of iterations and the coefficients value. So the coefficients values should ideally be same in all methods. The number of iteration of course will differ. The one that has lesser number of iteration is the one that should be preferred because that takes less computational power. So here is the final model that we have with us with the given data. So we have got three parameters in place. Beta naught happens to be 81.37, beta 1 is 102.68, and theta is 141.9. Okay, now you can explain this this coefficient from the model the way we explained the first slide, and then take a notice or use that as one of the explanation. The residual sum of square where we are getting these estimates is 39.2447, and then using this estimate you can write the final model. The final model looks something like this, with this intercept 81.37, slope coefficient 102.68, and the exponential coefficient to be 141.9. So given this equation, you just you can fit a regression line through this curve, and this is non-linear in nature. Okay, non-linear in nature, and it need not be just because it looks non-linear, just because we have fit a non-linear parameter. You can actually fit a polynomial regression as well. Okay, polynomial regression, and polynomial regressions are not necessarily nonlinear regression. Okay, they can be nonlinear if the parameters are not made to be nonlinear. Otherwise, if the parameters are linear and it's just the variables which are of nonlinear forms, which also can fit something a distribution something like this, is not linear. It rather said to be a polynomial one. So it's important to understand the difference between nonlinear and polynomial regressions. So to summarize, we use a nonlinear regression model when at least one of the parameters is nonlinear. So that's the important one to be remembered, that one of the parameter in the model should be a not linear one and should not be linear. Nonlinear regression is an iterative procedure. So you find the likelihood and iteratively you optimize the loss function and find it out. With the number of iterations depend how quickly the parameters converge. So if the parameter converges quickly, you get you get all the values with lesser number of iterations. Otherwise, it takes quite a lot of time. And there are three ways of doing it, and we have seen that, right? We have seen how we can use the three ways of computing, doing the optimization and getting the values of the coefficient. So that's a brief introduction to what is nonlinear regression, how it is different from polynomial regression and linear regression, and what are the ways in which you can compute the parameters of nonlinear regression. Thank you so much.